Well, good morning, good afternoon, or good evening, whatever time it is in your part of the world. Welcome to the web seminar on understanding FMEDA failure rates. A couple of notices. I'm going to type up a notice. Audio is provided via personal computer. Turn on the speakers on PC and on tab above. Another notice. Please use the Q&A tab to ask questions. In fact, many of you who have been to these seminars before know that I often ask the question, can you hear me? And please type back an answer in the Q&A tab. How well is the audio working? I'd like to hear if anybody Okay, so far I got a few answers. The audio is working fine. That's great. As you know, I like to check not only the audio, but do you use the Q&A tab correctly? All right. Thank you all. My name is Bill Goebel. I've spent most of my time, my professional career doing research and development, new product development. I've been involved in electronic hardware design, mechanical hardware design, software design, and engineering management. For the last 20 years, I've spent a lot of time studying reliability engineering and probability of failure. One of the things that we were very active in is the development, the creation and development of the FMEDA approach, which we will be talking about today. I'm not really going to get into any of the history of FMEDA, but briefly I'll mention this is an activity that a group of us started in the late 1980s, and we're still working on improving FMEDA results even today. I work for a company called exida. Exida is a global corporation with offices around the world. We have a lot of experts from new product development, certification, and end users. At exida, we do a lot of things. Support, services, consulting. There's a special group involved in product certification. We do a lot of training, including things like this web seminar. We have engineering tools to help people adopt the safety life cycle. Reference materials, we do a lot of research into failure rate data, and exida administers the CFSE professional certification program. If you're interested, please check out cfse.org. At exida, we publish a lot of material. Most of our reference material, including all of our databases, are publicly available. We do that for a number of reasons. We could keep this information as a secret company document, but that doesn't help make the world a safer place. It's better if the data is readily available. Now, we do charge money. That's how we pay for the research. And so hopefully you will benefit from our data. You know from this entire series of seminars, what we're really talking about is all important because of the probabilistic design-based approach in functional safety standards today, like IEC 61508. We must model probabilistic performance of our instrument designs. It can be done on a design example basis, but to get maximum flexibility and to optimize the cost of every safety installation, a risk based performance approach can be used. Unfortunately, or fortunately, the advantage of that approach is we can really do a fine job optimizing a design for a particular site. But we must have good failure rate data in order for this whole approach to work. Where do we get good failure rate data? There are a number of sources available, but data quality is important. The new version of IEC 61508 even has specific statements about data quality, allowing a SIL verification designer to avoid architectural or not even consider architectural constraints if the data is of sufficient quality. Now, the standard talks about 90% confidence, but it's a lot more than just use of a confidence interval in statistical analysis. It's really, do you have full confidence that the data collected is high quality? That's what the essence of Route 2H is all about. See a few more people joined us. Status screen still looks good. Let's keep going. At exida, we treat this data quality issue very, very seriously, and we spend hundreds of thousands of dollars every year on data research. And the clear objective is that field failure calibrated FMEDA data is absolutely the best source of failure rate data for any probabilistic performance-based design verification. However, you really must understand what is this FMEDA data and how do you use it. And that is the essence of our web seminar today. I use the term field failure calibrated FMEDA data. What I mean by that is that you can't, let me back up for a minute. I remember back in the old days, you know, the 1980s, when failure rate data for components came from a document called Mill Handbook 217. And the most recent version that I ever used was 217F. And we would look up the failure rates of resistors and capacitors and integrated circuits, and we would do board level reliability calculations, and we would come up with failure rates. And then I would read papers that said these Mill Handbook 217F numbers were very pessimistic. One particular paper from the industrial control community, from process control, indicated 217F numbers were 4 times worse than they should be. And that paper proposed field failure comparisons with 217F calculations. And to me, as a relatively new student to reliability engineering, boy, that makes sense. So at exida, we have been gathering up field failure data for 12 years now. And we've done over 100 field failure studies, representing over 10 billion unit operating hours. And every time we do a field failure study, we do just what the paper from the 1980s said to do: compare results. If we have a product level failure rate that comes from an FMEDA and field failure data for a similar product, obviously, you can learn something by comparing these numbers. I mean, they're supposed to match, right? And what happens if they don't match? If there's a significant difference, we must find the reason. Now, I will say in some cases the problem was in the field failure data collection, but in other cases the component database needed to be updated and recalibrated. When you have done enough of these field failure studies, and to me, 100 is far more than enough, the data in the component database starts to get very accurate in terms of predicting failure rates. The end result of all that is an electrical and mechanical component database that considers not only the environmental operating profile, but design-based characteristics. And so given a particular environment, we have a component-level electronic component database, which then can feed the FMEDA process to generate very accurate product failure rates, product failure modes, and diagnostic coverage parameters. I haven't seen any questions yet. Just stop to remind you, please do not hesitate to ask questions, make comments. If I say something you wish to challenge, do not hesitate. It's not an insult. It's good. FMEDA, the FMEDA results need to be done as a function of operating environment. Therefore, the component database has to be calibrated for a number of different operating environments. Currently at exida, we have 6 different operating environments: cabinet, control rooms, field equipment with both 2-wire and 4-wire operation. Fundamental difference being 2-wire devices have little internal power dissipation, where 4-wire devices might have several watts of power. And temperatures inside a case will, inside a component housing will be much higher than outside ambient. We do have an automotive environment, which is used, of course, for the automotive industry. And lastly, subsea and offshore topside. We got a question. Thank you. Are FMEDA results predicted data, or is it actual data collected from field experience? A good question. The answer is, it's both. Actual data from field, and that's the essence of this combination technique. Actual field failure data is sorted down to the component level, and the component level data is recombined during the FMEDA to predict failure rates of a product. And can you imagine now the advantages of that? What happens if you have a brand new product, a brand new design? By the time you get field failure data, the product may very well be out of production. So how do you get data for a new product? Answer, FMEDA. So thanks for the question. My answer is FMEDA is a combination of all the known information. The operating environment, the design characteristics of a product, and field operating experience. And in our case, 10 billion hours. Now let me go ahead and make sure you know what this FMEDA concept is. Rather than keep statistics for a product like a pressure transmitter or a valve actuator assembly or an entire valve actuator assembly with pneumatic controls, rather than keep statistics of a device which may have hundreds of components, let's keep statistics on the components. First of all, it'll be a lot easier to gather up specific failure rate data. Secondly, component data can be used to predict failure rates of new products. So instead of trying to keep statistics on products, which we need to keep anyway, of course, for many reasons, but that was a previous seminar, Let's get the failure rate data for the components. Given a component database, you go through a process of looking at a product one component at a time. For example, if this capacitor, this one, fails open circuit in this electronic assembly, what is the impact? And we will look at that impact, study the electronic design, and in all likelihood it might have no impact, except increased noise levels, which may or may not impact the safety functionality of a product. But if, for example, that capacitor failed short circuit, it would take out a power supply, probably take a current on a 2-wire transmitter to full scale, and we note the impact of every single component in a design. That's what I mean about taking thorough advantage of all the design knowledge available for a particular product. Now the question, what does a component database comprise? Good question. For every different kind of component, the failure rate of each component is listed as a function of each operating environment. The failure mode distribution of each component is listed. And for example, for a resistor, it might be open circuit, short circuit, drift high, drift low. All known failure modes of all components are listed in the database as a function of operating environment. Just check here. Okay, that's all the questions for now. Thank you for asking, and all comments are always appreciated. Given that we've done an FMEDA on a product, we generate the product failure rate. Even if it's a brand new design, we'll be able to have failure rate information long before field failure rate data will ever give us the information we need. We thoroughly understand the product failure modes and the diagnostic coverage of any given design. FMEDAs, or especially the diagnostic portion of an FMEDA, must be backed up with good fault injection testing to make certain that the FMEDA results are accurate. Now, for those of you who are thinking ahead, you've already recognized a problem. The biggest negative in the FMEDA is the component database. What if the component database is no good? Well, obviously the results will be questionable. Therefore, it's essential that any component database used has to be based on and calibrated by field failure data. So hence, my earlier answer to the question, is FMEDA predictive or is it based on real field data? The answer is both. Now, I told you about the biggest negative in FMEDAs. And in fact, all FMEDA/FMEA results being published today are not the same. Take a look at these numbers. The first three numbers are for a ball valve. FMEDA results done by exida with the field failure calibrated database show a number as low as 4.8 e to the minus 7 failures per hour, or as high as 1.35 e to the minus 6. It's not quite an order of magnitude. What's the difference? It has to do with the operating application of the valve. Do we need tight shutoff, or is the valve fully functional even when there is some seat leakage? Certain failures of the seat, therefore, don't count. Check questions. Nothing new? Okay. However, On line number 3, there's another number for a ball valve. 6.5 times e to the minus 8, that's almost an order of magnitude lower than the lowest number we've seen so far. Is this a super ball valve manufactured by a super company? We have to find out. Or was there some other method? Is the component database used? Not so good. What about, here's another set of numbers, actuator numbers. These are 3 numbers for rack and pinion spring return actuators. Exida FMEDA results become in between 4 and 6 times 10 to the minus 7. And another number published by another certification agency came in at 9 times 10 to the minus 9. That's a very low number. Wow, this must be some super design. What do you think the problem is? I have a clue for you. Two of these numbers are based on manufacturer's warranty data. When I worked for a manufacturer, I was taught to make certain assumptions, all of which provided nice numbers that made the product look great. There's a paper on this subject on the exida website, so don't hesitate to look up the paper, failure rate data, the good, the bad, and the ugly. The ugly is manufacturer's warranty data, because in fact, it's the assumptions. Now, we did cover that in last week's web seminar, and anybody that didn't get to hear that can listen to the recording on the exida website. Another thing one can do is the same thing that was done in that paper I read back in 1980s. Compare predicted results with field failure results. We do that quite a bit at exida. And I look at the numbers for analog pressure transmitters. And I see numbers running, total failure rate running about 5 times 10 to the minus 7. And FMEDA results for 2 different analog pressure transmitters without a remote seal come out roughly 4 times 10 to the minus 7 to 8 times 10 to the minus 7. And you might say, what's the difference between those 2 designs? And there is a substantial difference in the complexity between those particular designs. The old 1151 is a classic analog pressure transmitter design from the early 80s, and the 1152 is a very special design for the nuclear industry, which doesn't use op amps. It's only discrete transistors. It has a higher failure rate and a much higher dangerous undetected failure rate. These results seem somewhat comparable. They're not that far off from the Dow study, which is a number between roughly 3 and 7 times 10 to the minus 6. But that study doesn't indicate whether the failure rate includes such things as impulse line or remote seals. In fact, when you include remote seals, even FMEDA results start coming up in value, of course. And that's one advantage of FMEDAs. There's absolutely a separate failure rate numbers for impulse lines and remote seals and all the other accessories that go with a pressure transmitter. Now, these numbers don't look too bad. One number looks particularly high compared to FMEDAs. Well, it's not too far off, but The OLF 070, which is based on OREDA, failure rate data from the North Sea, has a dangerous undetected failure rate very similar to FMEDA results, at least for analog transmitters, the older designs. But the numbers for newer designs, especially the safety certified designs, the DU failure rate is much higher. I find that to be completely consistent and logical. Field failure data typically is not available on a new product for many years. And so obviously the OREDA data is based on technologies that is many years old. The other thing is field failure data often does not include an indication as to whether the failure was detected by an automatic diagnostic or by a proof test or some other mechanism. And so there's no real way to separate the dangerous detected from the dangerous undetected in most field failure data systems. So I find this data to be overall quite comparable, especially when you understand that OREDA data includes maintenance-induced failures. I had a chance to visit Norway a few weeks ago and discuss these issues with people who were part of the OREDA analysis team. And they argued, not really argued, but it was stated very clearly that maintenance-induced failures, maintenance-induced random failures, are an important part of a safety performance-based verification system. exida completely agrees. However, one study done by exida found a 4x difference in the failure rate of the exact same piece of equipment based on maintenance-induced failures. 4x? That's very interesting to me. But it's not an attribute of a product. It's a failure rate or a failure probability attribute of a site. The maintenance training, the maintenance culture of a site, not a product. And therefore, it certainly does not belong grouped with a product failure rate. One other major comparison of FMEDA data to field failure studies was done by Numor in Germany. And in this particular study, although the information was not in a directly comparable format, a PhD thesis was published with some nice detailed data, and failure rates could be reverse engineered. And that particular study indicated that sensing devices, the FMEDA data was slightly higher than the Numor data. For logic solvers, the FMEDA data was slightly higher, 20 to 30%. And I think that's pretty good. But this particular study said FMEDA data for valves and final element is way too high. It was not possible to dig into the details of this because the particular failure study was classified as confidential. So no one at exida was able to dig in and understand why. But I think it's a very good thing when you're being criticized for both being too high and too low. It's very important to understand what is not included in the FMEDA failure rate. There are certainly two things that are not included. Well, three things. Number one, maintenance-induced failures are not included as a product attribute. They should be modeled, and in fact in the exSilentia tool, they are modeled with a separate mechanism which we call maintenance capability, which is site-specific. Systematic failures are not included. Many field failure data studies include failures due to faulty designs or faulty maintenance procedures. And it is very important that those failure records be recorded so that improvements can be made, corrective action can be made. Secondly, wear-out failures are not included in an FMEDA. Instead, a useful life parameter is published. 61511 says that useful life parameters must be published by manufacturers, and 61508 said useful life parameters must be established, and 11 says you must do predictive maintenance, replacing or refurbishing equipment when the useful life has expired. None of these issues are included in FMEDA data, nor is it appropriate to associate these with a product useful life random failure rate. Now, I did mention that it is important to take care of maintenance-induced failures. If you don't include this information in your safety verification, you may very well be designing a system with insufficient safety. In the exSilentia software, we solve this problem with a set of parameters called maintenance capability. And in the exSilentia tool, we allow you to set the maintenance capability separately for sensors, logic solvers, and final elements. One of the reasons for that is that the control room equipment often has better maintenance capability than field equipment. And it's not just the operating environment, it's that people do spend a lot more time paying attention to the controller, especially when its failure may take down an entire plant. I mean, the critical nature of the device dictates that it get high maintenance priority. In the exSilentia tool, a series of questions are asked, and depending on the answers to those questions, one of 5 different categories is given, MCI 0 through MCI 4. And you can read the descriptions of these different maintenance capabilities. No repair, medium, good, almost perfect, and perfect repair. This has an impact on probability. Maintenance capability has an impact on probability of failure, probability of repair, probability of achieving proof tests on schedule. There's a number of variables rather than just failure rate that are impacted by maintenance capability. Now the problem is, if one is using simplified equations, including the equations from IEC 61508 Part 6, and many of the tools, the SIL verification tools on the market, simply use the equations from 61508. And these equations make a number of very optimistic assumptions, including, of course, proof test capability and maintenance capability. If you're going to use these equations, then you most certainly have to add additional probability of failures to FMEDA numbers before using them. What kind of numbers? Well, I can give you an example by taking a look at maintenance capability impact from the exSilentia software. I did a very simple safety instrumented function with some redundant sensors, a SIL3 safety logic solver, and redundant final elements. And I set the maintenance capability to perfect. Our maintenance is 100%. Now, this effectively allows the tool to ignore maintenance capability. Now, take note that without changing any other variables, I got a PFD average of 5 times 10 to the minus 4 for my given set of parameters. And in this case, all 3 design barriers indicated I would meet SIL 3. Mean time to fail spurious was 77 years. All right, what's that look like if I take the maintenance capability down to basically no capability for the field and medium capability for the logic solver? My average probability of demand has dropped down to 4 times 10 to the minus 3. That's a pretty significant drop. Not quite, but let's go back and take a look again. 5 times 10 to the minus 4 compared to 4 times 10 to the minus 3. Wow. Order of magnitude. The SIL level, based on PFD average, has dropped to SIL 2. That's a clear indication that this maintenance capability could change numbers by an order of magnitude. Now, what that really means is, if you're using FMEDA data, you probably should at least quadruple the data. I'm honestly just estimating right now, because we have to, our research objective at exida is not to show you is not to figure out how to compensate for lack of detail in simplified equations, but to create highly effective, accurate models for highly effective methods like the Markov models used in exSilentia. So you see what's happening here. Maintenance capability is important. If the OREDA data includes that, then FMEDA results are perfectly aligned with OREDA data. I did ask some of the experts from SINTEF if they had separated the maintenance failure from the product-specific failures. They had not done that, but I was verbally told that, quote, a majority of the failure reports were due to maintenance-induced failures. I don't have any data to support that other than a verbal statement. Any other questions or comments here? Haven't seen any for a while. All right, well, the essence of the program today is field failure calibrated FMEDA data is the best data one can get for doing probabilistic verification of a safety design. The kind of information you get is very detailed, especially in certified products. Very detailed information of different failure modes, including diagnostic failure modes, if you wish to model to that level of detail. FMEDA results, however, do not include maintenance-induced and other site-specific failure attributes. They do not include systematic failures, which shouldn't be included in a probabilistic analysis anyway, but should absolutely be tracked and corrected. And lastly, FMEDA results do not include wear-out failures merged in with the useful life random failures, but a separate parameter for useful life. If anybody else has any questions, I very much appreciate taking a moment to type them up. If you find you have some questions tomorrow, next week, please do not hesitate to send an email. Questions, comments, anything you have to say, and we can answer. Sometimes it takes a few weeks to get an answer, but we do our best. Just checking to see if I have any more questions. I had one here. Do you also provide the safe failure fraction PFH result in the FMEDA? Many FMEDAs themselves deal with products that are substantially smaller than the element level as defined in 61508. Therefore, it's not appropriate to publish a safe failure fraction for a component. Architecture constraints are not intended to be applied for each separate component in a design. However, all the numbers one needs to calculate SFF for a 61508 element are absolutely included. In some products, the safe failure fraction is calculated as, for example, a single pressure transmitter could be used as an element in a safety function design. So for all the products where usage as an element is appropriate, safe failure fractions are absolutely published. PFH. PFH is a function of the application demand rate and can be calculated directly from FMEDA numbers depending on how rapid the demand rate is. For example, for continuous demand, you take FMEDA results for lambda dd and du and add them together. For PFH, for a high demand system, PFH equals lambda du. But we have a whole nother subject on high demand safety functions, so watch for that in our upcoming schedule. Another question, is the operational environment selection available in the exida software? Actually, right now it's an attribute of the product. For example, a 2-wire pressure transmitter is considered process industry 2-wire. A 4-wire flame detector, for example, is considered field equipment 4-wire. In the very near future, some additional application environments will be included in future releases of exSilentia, including offshore, topside, and subsea. Those are the two new areas where we are now working on updating the exSilentia software. Good question. Thank you. Let me just check to see if I see any more. I don't. Well, remember, don't hesitate to send an email if you have any other questions or comments. And I thank you very much. I hope you found your time useful. Thank you for attending, and goodbye for now.